This is the final presentation of the Gulf Coast Carbon Ore Rare Earth Element and Critical Mineral Initiative that was funded by the Department of Energy. And we are going to present the findings from this study. And with me today are Nolan Thaker from University of North Dakota and Brent Elliott from Bureau of Economic Geology. I'm going to share my slides. So this study was conducted from October 2021 to March of this year, and with a budget of $2 million, and was funded by Department of Energy and National Energy Technology Lab. So the main findings from the study are the following. The Gulf Coast coal resources that Peter Warwick and Bob Reedy mapped total 83 billion metric tons or gigatons in the upper 300 feet or 90 meters. 40% of those resources are found in Texas, 24% in Mississippi, 14% in Louisiana, and the remaining less than 10% in each of the other states. The rare earth element concentrations were variable, with some hotspots up to 3,000 parts per million of rare earth elements and yttrium. And the extractability that Nolan Thaker will talk about is high from these brown coals or lignites, 63 to 93% extractable with weak acids. The median rare earth plus yttrium as oxides is 129 parts per million, and an estimated $262 billion for the 83 gigatons, assuming 70% extractability. And then a lot of people are interested in certain rare earths, including praseodymium, neodymium, terbium, and dysprosium. And those oxides, the median value is 28 parts per million and result in a total value of 216 billion for the 83 gigatons of coal found in the Gulf Coast. So you can see that these rare earths constitute most of the value of the rare earths plus yttrium in the Gulf Coast, and they're very important for permanent magnets. We also looked at coal ash resources, and Bob Reedy mapped the coal ash resources throughout the US from the various basins, the Appalachian, Illinois, and Powder River Basin coals. And he evaluated the total coal production from 1950 to 2021, and that totaled 52 billion metric tons or 52 gigatons. And the ash related to that coal was an average of 10% of the coal, about 5.3 gigatons of ash throughout the US. And about 70% of that is potentially accessible, meaning that it has not been used on site or sold. Then the rare earth elements plus yttrium oxides in Appalachian, Illinois, and Powder River Basin coal ash totaled $8.4 billion and about 0.65 billion in the Gulf Coast. And the permanent magnet of rare earths totaled $5.2 billion and 0.4 billion for the Gulf Coast samples. We also looked at coal ash in the Gulf Coast from lignite, and the median rare earth concentration in coal ash is 4 times higher than that in the raw coal, because the rare earths are concentrated when you burn the coal and remain in the ash. And we estimated about 0.26 gigatons of coal ash from lignite in the Gulf Coast, and the rare earth element oxide value is about $0.26 billion. And the permanent magnets are about $0.9 billion, assuming 30% extractability of these rare earths from the coal ash. So the extractability from the coal ash is much less than that from the coal. Then J.P. Nicot and his colleagues looked at produced water, and Brent Elliott and others looked at produced water in brines. And using 2023 data, then the Permian Basin generated about 6.6 billion barrels of produced water. And the average lithium concentration in that was about 15 milligrams per liter. And that would represents about 16,000 tons of lithium and an estimated value of about 126 million for 2023 production. Brent Elliott and Rich Kyle looked at red mud from alumina processing from bauxite in the Gulf Coast sites and focused particularly on the Copano, site in Copano region. And that was 150 million tons of red mud. And from 16 samples, the rare earth element concentrations are very high, about 10 times, more than 10 times that in the upper continental crust, and result in a value of 3.4 billion for rare earth elements per yttrium oxides, and assuming 30% extractability. And the permanent magnets would represent about 2.7 billion. And heavy mineral sands from frac sands that Brent would be talking about, and zeolite and graphite also represent additional sources in the Gulf Coast. So I will hand off to other people to talk about different parts, but I'll just briefly talk about the coal and the coal ash. So this is a typical open pit mine, San Miguel mine in Texas. All of the coal mines in the Gulf Coast are open pit, and then we quantified, Bob Reedy and Peter Warwick, they quantified coal and coal ash resources as feedstocks, and then measured the rare earth element concentrations and critical minerals. And then in this project, of course, as I just showed from the findings, we looked at produced water, we looked at bauxite residue in red mud, and we looked at heavy mineral sands, zeolite, and graphite. And then this project provided an opportunity to connect with industry, and we'll describe that throughout the presentation. We developed planning to develop a technology innovation center or different centers related to various feedstocks. And then we did stakeholder outreach and education also to support workforce development and economic development. So there were 7 tasks: project management, based on assessment of CORE-CM resources, strategies for reuse of waste streams, and the waste streams were the coal ash, red mud, graphite and zeolite and heavy mineral sands, and then looking at strategies for infrastructure, industries and businesses that Brent led, and then technology assessment, development and feed testing that Nolan helped a lot with, and potential technology innovation centers and stakeholder outreach. So the University of Texas Bureau of Economic Geology was the lead organization, and other team members included the U.S. Geological Survey, Geological Survey of Alabama, University of North Dakota, College of Engineering and Mines, University of Kentucky, and University of Wyoming. So it was really nice team because we benefited teaming with North Dakota. They also have similar coals as we have in the Gulf Coast, immature brown coals or lignite. And so it was great to team with them because they've done a lot more work on extracting rare earth elements from these coals and developing bench and pilot scale testing. And then working with the University of Wyoming, Daveen Bagdonas, that was very helpful because we burn a lot of Powder River Basin coals in the Gulf Coast. And so understanding the ash deposits and rare earth elements from Powder River Basin coals was very helpful. And then we connected with the various industry and government and research resources, and then collaborated with the National Energy Technology Lab and working with North American Coal Company and Element USA. So this is the team. I'm Bridget Scanlon. Brent Elliott will be talking today, and Bob Reedy, JP Nico, Rich Kyle, and Tristan Childress, all from the University of Texas, and then Peter Warwick from U.S. Geological Survey, and Jim Howe from University of Kentucky, Daveen Bagdonas from University of Wyoming, and Nolan Thaker from University of North Dakota, and Sandy Ebersol and others from Geological Survey of Alabama, and Dennis James, who worked previously with the North American Coal Company. So here you can see the various basins, coal basins throughout the US. And so we're going to be talking about the Gulf Coast Basin shown in yellow, and that is because it's a lignite brown coal, immature coal. And then you can also see that the Williston Basin in North Dakota and surrounding states is also lignite. Then you've got very little anthracite and low volatile bituminous, but you've got medium and high volatile bituminous in the Appalachian Basin in Illinois, and the Midwest region, and then subbituminous coals in the western U.S., Powder River Basin, the Green River, and other places in the west. So Department of Energy developed a critical mineral list for energy, and this is the 2023 data. And on the left, you can see short-term, on the y-axis is the importance to energy, and then on the x-axis is the supply risk. So you can see the elements that are high supply risk and high importance to energy are these rare earth elements, neodymium, terbium, iridium, and then also graphite, gallium, and cobalt, and then very high is dysprosium. So these are dysprosium, neodymium, these are used for permanent magnets. And so others are in the other quadrants. And for the long term, the medium term, then 2025 to 2035, you can see all of the heavy, the rare earths that contribute to permanent magnets are listed in the upper right quadrant, and also lithium also listed on high supply risk and high importance to energy. So we are talking about unconventional resources of rare earth elements, but in this graph, the Department of Energy compared rare earth element levels in conventional ores to unconventional resources. Brent, would you like to talk about this?
Sure. Yeah. So in the graph, you can see the concentration of the rare earths individually, along with scandium and yttrium. Across the x-axis, you can see the individual constituents. Mount Weld in Australia and Mountain Pass in California are in the kind of the green and black symbols on the graph, and show substantially higher values but that's conventional mining and the conventional material that comes out of the ground in those processes. By comparison, look at the kind of the AMD or the acid mine drainage waste that kind of getting out of West Virginia, the coal refuse from the University of Kentucky, and then the coal ash and sedimentary rocks by comparison, and the U.S. coal. So there's a substantial amount of unconventional rare earths that are available within the coal materials compared to what we have in Mountain Pass and Mount Weld.
So looking at the basinal assessment of coal critical mineral resources, Bob Reedy and Peter Warwick mapped the coal thickness and leveraged the data that the US Geological Survey had mapped, Peter Warwick had mapped earlier and published in 2011, and added additional data. So ended up with about 31,180 drill holes and other data. So they developed regional maps of total coal thickness across the basin in the upper 300 feet. And then we analyzed 118 samples, coal samples. 60 of those samples were archived in USGS headquarters, and the others were collected, some collected by the Geological Survey of Alabama, others collected from Louisiana and Mississippi. North American Coal provided some samples, and San Miguel mine, an active mine, we collected additional samples. And then Nolan Thaker looked at the extractability of the rare earths from the coal and coal ash, and he will talk about that. So here you can see a map showing the distribution of the coal-bearing zones and the coal mines. The coal mines are shown in black in different parts of the Gulf Coast Basin. And you can see the Wilcox group along this band here throughout, and then you can also see the Jackson group is another major unit that includes coal mines. So they mapped the coal resources throughout the Gulf Coast, and so these are the various points that were used to map the 31,180 points, and then they were subdivided into different regions, the eastern region shown in red, the northern region, and the western region, and they used kriging then to develop a resource assessment. And so this is the map of the coal thickness from the different units, and you can see thicknesses, cumulative thicknesses in the upper 300 feet of 4 to 5 meters or 15 feet along these bands, and also in East Texas and Northwest Louisiana. And you can see the trends along the different coal-bearing units. And based on these data, then they estimated there was 83 gigatons of coal, that billion metric tons of coal, that's coal resources in the upper 300 feet. And that's because most of the coal mining in the Gulf Coast is open pit mining. And so 300 feet was considered reasonable. And so this is the distribution of the coal in the different regions. So 40% of the coal is in the Texas region, and these different bars represent the different depths. So 15 meters is the green bar, and the dark blue is 90 meters or 300 feet. So as you look at a greater extent, then you see more and more coal. So 40% in Texas, 24% in Mississippi, 14% in Louisiana, and 10% or less in the other states. And then this is the depth below the surface, and so you can see that the total coal resource increases with depth, and so 83 gigatons at 90 meters depth or 300 feet. And so we've got about 5 active mines in the Gulf Coast region: San Miguel, Calvert and Cossey, 5 Forks in Louisiana, and Red Hills in Mississippi. And this is the distribution of samples that were collected for rare earth element concentrations, and about half of the samples were derived from archived data from the USGS headquarters in DC. And here you can see this is the 118 samples on the y-axis, and this is the concentrations of rare earth elements. And you can see the different colors represent the different elements. So blue is lanthanum, red is cerium, etc., all the way up to scandium. And so you can see very high concentrations in the Gibbons Creek area in Texas, and lower concentrations, generally less than 300 parts per million in many of the other regions, with some localized hotspots. And so you can see the Gibbons Creek sample, we've almost up to 2,800 parts per million of total rare earths plus yttrium plus scandium. So the median rare earth plus yttrium is 110 parts per million, and the range is 18 to 2,862. And Gibbons Creek is a hotspot, and median concentrations are generally less than the upper continental crust, and the mean is similar to the upper continental crust concentrations. So this is on a dry coal basis. This is the raw coal. And so here is a box plot then showing the distribution of concentrations for each of the rare earth elements, and the rare earth elements plus yttrium on the right, the sum of those. And you can see the mean is in red, and the median is the black bar in the center. And you can see 1 is would correspond to the upper continental crust. And you can see the median is less than the upper continental crust for most samples, and scandium is lower than most of the other rare earth elements. And the mean is somewhat higher in some samples, and then quite a wide distribution. And so, Nolan, would you like to talk about the extractability then?
Yep. So we did some experiments using essentially a sequential extraction method to identify what level of the rare earths would actually be recoverable or extractable from the lignites. So we looked at the Gibbons Creek sample, multiple San Miguel samples, and then the ash produced from the San Miguel, fly ash produced from burning the San Miguel coal. In general, we saw really high extractability across the board for the rare earths, with the exception of occasionally scandium in dilute acids from the rare earths, apart from the fly ash, which was considerably more difficult to extract from. This corresponds similarly to what is found in other lignites, such as in North Dakota, where the rare earths are considerably this plot, where the rare earths are considerably more extractable in that kind of dilute acid soluble organic coordination group than essentially discrete minerals that are much harder to dissolve. We'll note the lower extractability of all of the rare earths slightly than North Dakota, which could imply there's another method. There could be some mineralization occurring, but in general, there's relatively high extractability. and also noted that the germanium and gallium is extractable, although at much lower levels, mainly due to the germanium and gallium having potentially different forms than the rare earths, particularly around pyrite inclusions.
And Nolan, do you want to mention that the high extractability is because the rare earths are in the organic phase?
Yep. So that describing that organically associated phase, the rare earths in lignite, from what we've determined, are largely actually bound into the organic phase of the lignite, binding to carboxylic acid and sometimes phenolic groups within the lignites rather than in discrete minerals. That enables a much easier extraction, both with the amount of chemicals required and also the time involved, but it also typically involves a much higher level of extraction than would be typically seen of minerals, where you have a variety of minerals that require different grades of, or different concentrations of acids and different times to dissolve fully. The lignites generally are much faster to extract from. For instance, extractions of 50 to 60 to 70% is possible with as little as 15 minutes rather than multiple hours to days of extraction time typically, mainly due to that organic character.
Right, and that's really important. And so it's nice that it seems that the Gulf Coast lignites seem to be behaving similarly to the lignites in the Williston Basin in North Dakota. And that high extractability is very favorable. But then when you burn the coals and create the ash, then the rare earth elements go into possibly a silicate phase. And then that's much more difficult to extract, as Nolan shows with his analysis. So I think we can learn a lot from Nolan and his team work up in North Dakota and apply some of those results to the Gulf Coast, which would be a huge help. And so then we also wanted to look at the value of the rare earth oxides in the Gulf Coast coal. So on the left here, I showed the prices of different rare earth elements over time. You can see that scandium is the highest, and the y-axis is the price in dollars per kilogram. And this is a log scale, so scandium is generates a high price. And then the magnets, terbium, dysprosium, praseodymium, and neodymium also generate quite high prices, about $100 per kilogram for praseodymium and neodymium, and higher prices than for terbium and dysprosium. Lanthanum and cerium generate very low prices, almost nothing. Some people almost consider them a waste. And on the right, then, we can show the concentrations of the rare earth oxides for the permanent magnets, the rare earth elements plus yttrium, and then you can see the value. So the median value for the permanent magnets is 28 parts per million is oxide, and the median value for rare earths plus yttrium is 129 parts per million. And then we also estimated the value per ton of coal that contains these rare earths, and it's about $4 per ton, a median value for the permanent magnets, and about $5 for the rare earth elements plus yttrium. And then considering 83 gigatons of coal in the Gulf Coast, then we come up with a value of about 216 billion for the permanent magnets and 262 billion for the rare earth elements plus yttrium. So I guess I just said all of that, I guess, and that assumes so this assumes the extractability that Nolan showed earlier. We assumed 70% extractable from the coal. Then the third task was based on strategies for use of waste streams. And the first one is coal ash, and then Brent Elliott will talk about red mud, heavy mineral placer deposits, zeolites, and graphite. And we've finalized with talking about lithium from produced water and brines. So these are the coal basins throughout the US, and Bob Reedy estimated how much coal ash was derived from different coals throughout the US in the power plants. And looking at those data, then this is the coal ash in the US, and this is the time series. So the red is from anthracite, the blue is bituminous, the green is subbituminous, and the black is lignite. So Bob estimates that we generated 52 billion metric tons or gigatons of coal from 1950 to 2021. And then about 10% of that on average became ash. So that was 5.3 gigatons of coal ash from over this time period. And that 10% on average, but by bituminous coals only generate about 60% ash, whereas lignite generates about 14% ash. And then looking at the disposition of the ash from the Energy Information Agency, found that about 70% of the coal ash is potentially accessible. That means it hasn't been used or sold, used on site or sold. And then looking at the concentrations of rare earth elements from Taggart's data from the Appalachians, about 585 parts per million rare earth elements plus yttrium plus scandium. Illinois and Powder River Basin are lower, about 280 to 330, but the extractability varies. Appalachian and Illinois is about 30% extractable, and Powder River Basin has higher extractability because of high calcium in the ashes from the Powder River Basin. It's about 70% extractable. So the black line is the total ash. The red line on this graph is the accessible ash, and then the lower red line is accessible and extractable. So considering that, then we estimated the value of rare earth elements from coal ash from these three basins, Appalachian, Illinois, and Powder River Basin, and came up with a total value of $8.4 billion, considering accessibility and extractability and the concentrations in the different basins. So, so that's in the ash, and then comparing the ash to the coal, then this is in the Gulf Coast samples. We had 118 samples, and so the black line, the solid black line, is the rare earth elements plus yttrium on a dry coal basis, and then the dashed line, if you divide the rare earth elements on a dry coal basis by the ash content, you get the corresponding rare earth element plus yttrium concentrations in the on the ash basis. And so you can see the average, rare earth elements in the ash basis are about average 4 times higher than that in the coal, because you're concentrating the rare earth elements when you burn the coal, and you're left, and they remain in the ash. So then comparing the values of the rare earth oxides for coal versus coal ash. So on the top, we've got on a dry coal basis, and we've got the permanent magnets and the rare earth elements plus yttrium. And so this is I'll just focus on the median values. So this is the concentrations we just talked earlier about on a coal basis, and we came up with the permanent magnets being $216 billion, and the rare earth elements plus yttrium, $262 billion. On an ash basis, then we come up with a value of $0.9 billion for the permanent magnets and $1.1 billion for the rare earth elements plus yttrium. And that's based on 0.26 gigatons of coal ash potentially accessible from lignite in the Gulf Coast, and to 30% extractability from coal ash, whereas we had 70% extractability from the coal itself. So you can see that there's trade-offs here. There's low concentrations of rare earth elements in coal versus coal ash, about 4 times lower, but there's higher extractability of rare earths from coal versus coal ash. So they kind of balance each other out. So Brent, go ahead and please talk about the red mud.
So the Texas Gulf Coast hosts 5 different sites between Texas, Louisiana, and Alabama. There are 2 in Texas at Copano. That's one to the farthest to the south near Corpus Christi, the old showroom facility. And then there's the one at Point Comfort there off of Lavaca Bay, and kind of in the mid part of the coast. And then there's Gramercy and Burnside, which are in Louisiana, and then Mobile Bay over in the southern part of Alabama. So we were able to sample about 23 samples from Texas facilities, most of them coming from the Copano facility, and then lesser amount from the Point Comfort facility in the central part of Texas, and then a sample from Gramercy in Louisiana that was donated to us by Element USA. So we completed geochemical analysis and microanalysis of these samples. You can see from the sites, the different pictures of the satellite imagery there in Copano site and the Point Comfort. Those are the large impoundments, and most of that material is coming from Jamaica and Brazil. So Gramercy and Copano site in Texas have a very similar kind of makeup, and Point Comfort had a little more of the Brazilian sourced bauxite material. And so its compositions are a little bit different from what we were able to tell from the geochemistry. So most of the high values that we see are from the Copano site and from Gramercy. Sometimes the total rare earth and yttrium content being close to about 3,500 ppm. In the Point Comfort material being an order of magnitude less than that, less than 500 ppm. So it's a pretty significant difference between that red mud material. Similar box plot as Bridget explained for the coal material relative to the upper continental crust normalization value. The median value and the mean values are shown in those box plots. You can see kind of the ranges are pretty consistent across all of the rare earths, and pretty. And Bridget, I don't know if you remember from
this is the Copano site. This is the high site. Just
the Copano site, yeah. So with the median Copano site being about close to 2,000 ppm at 1988. And the praseodymium, neodymium, terbium, dysprosium values equaling about 428 ppm.
Right. And yttrium, so most of these are about over 10 times the concentration of the upper continental crust. Whereas before, when we were looking at the coal, we were doing around less than 1, so less than the upper continental crustal values. But here, more than 10 times. And then yttrium is more than 20 times. Scandium is fairly rich also. And that's the total.
That alumina processing waste, right? So this is another example of the different beds and impoundments along the coastline within the Copano site in Texas. Represents about 150 million tons of that bauxite residue or alumina processing residue, assuming about 30% extractability. With the rare earth concentration about 2687 ppm, right? That's a value of about $3.4 billion. And if you just look at the rare earth elements that are of interest for magnets, praseodymium, neodymium, terbium, and dysprosium, right, medium concentration about 520 ppm, and it's a significant amount of that total, about 2.7 billion in revenue generated from that. So we also looked at some X-ray computed tomography to look at the different attenuations and different densities of material within that material, with the idea that we're trying to hone in on what specific minerals are hosting the rare earth elements in yttrium, and to see if we can work out, in the future, some possibilities for further processing, further either mechanical or chemical processing that get those concentrations higher and some beneficiation of that material to make the extraction process more affordable and more efficient. In the lower pictures, go back.
Oh, sorry.
So for the EDS images or the composite false color map that you see there on the bottom, you can see the different mineral grains that represent, that red color on the right hand, being some quartz grains. So we're looking at different SEM and geochemistry of the specific minerals within those to characterize them and become familiar with what's the specific mineral hosts, to eliminate the stuff we don't want and be able to concentrate the things we do want. One of the things I think that's probably important is that there are other revenue streams or secondary or even primary mineral commodities that can come off of this: titanium, iron, scandium. In addition to rare earth elements and yttrium that can make this feedstock as an important source for extraction. So heavy mineral sands, are all across the state of Texas. And we look primarily at Texas for this purpose. There's a lot of mines across the Llano Uplift in central Texas that have historically produced hydraulic fracturing sand. that fed into the frac jobs all across the Eagle Ford Basin and the Permian Basin and the across the whole Gulf Coast region, really. But in more recent years, with the I guess the development of new mines out in West Texas that feed that hydraulic fracturing sand need, a lot of those mines are really looking for some way to stay in business and sell their sand material, and the heavy minerals, are one way of doing that because they offset costs and it's a waste stream for them, but they have a lot of potential for development. We take that material, that waste stream, and run it through a spiral, mechanically separated by density, as well as these gold tables, and mechanically wash them across the table and get heavy mineral concentrates that are showing up to 1% or above of heavy minerals, as well as the total rare earth concentrations. Did I have another picture of that one? So the example of heavy mineral concentrate under a petrographic microscope, and you can see that you have lots of magnetite, ilmenite, but a lot of zircon, in the range of 4 to 23% of that simple material. Those heavy minerals compose about, typically around 2% of the mine material that goes into that waste stream. And you get things like zircon and monazite and titanite, that contain those rare earth elements, and deuterium, or other things like iron and titanium that are of interest. It's estimated to be about 178 million tons of that sand resource, and about 4 million tons of heavy mineral concentrate, within that source, that feedstock, or about 160,000 tons of rare earth elements and deuterium. Another feedstock of interest is zeolite. The actual ash deposits that are across the Texas area. And you see a number of those red dots represent prospective areas, and then the black stars are actual active sites that are in operation or close operation. Those that the bridge is pointing out in South Texas, those are in operation and produce a majority of the zeolite material from the Catahoula ash material in Central Texas. And then there's one out in West Texas that's being developed, currently. Of those prospective sites, 16 of them in total. You can see from the box plot down there that they're a little bit on the order of magnitude, probably less than what you saw with the bauxite residue, but still elevated compared to the coal ash. Do you have any comments to make about that other than the?
No, I mean, for the bauxite residue, we were over 10 times, and now we're
10, 20.
down around upper continental crustal values again. Yeah.
So another feedstock of interest being part of the CORE-CM initiative for carbon ore, rare earth element, and critical minerals. We're looking at graphite is of major interest. The area in Alabama and the southern Piedmont just had a survey that was done by the USGS to kind of delineate a lot of that area, that district. We also have a graphite district that was historically mined and produced and prospected in Central Texas, around the Llano Uplift, specifically around the northern flanks of the Llano Uplift, where the Paxel schist and the Henry Creek Formation within those metamorphic rocks, and they're about older than their Precambrian age. So samples that we were taken from the tailings material, is that mine waste material. About 12% of the prospective ore body and delineated zones.
Sorry, I got to give you a graph.
There's still about 2 million tons of remaining material within that, contain about 3.5% graphite. And those tailings materials is mainly in graphitic clay, 2 to 18%. You have mined the flake graphite within there is typically around a little bit greater than 80 mesh, and those tailings contain primarily flakes of 50 mesh or so.
Thanks so much, Brent. And so now we'll just talk a little bit about lithium in oil field waters. And this is work that Roxana Darvari and JP Nico and others and Brent also did, looking at the lithium concentration. So here you can see lithium concentrations. The black small circles are very low concentrations, and the purple with the red boundaries are much higher concentrations. So you can see very high concentrations in Arkansas, southwestern Arkansas, related to the Smackover, and then other potential sources are Smackover that extends into East Texas. And maybe, Brent, you should be talking about this. And then the Deep Edwards, and then the Permian Basin. This is the Midland Basin and the Delaware Basin within the Permian Basin. The Permian Basin generates a lot of produced water, very high volumes of produced water. And so in 2023, about 6.6 billion barrels of produced water were generated by the Permian Basin, but the lithium concentrations are very low, so about 15 milligrams per liter. But so, and that would result, represents about 16,000 tons of lithium per year, and would generate a value of about $126 billion for 2023. So the concentrations are low, but there's a lot of work being done on treatment of produced water because of induced seismicity concerns, and trying to find other ways to deal with the produced water. And so if they come up with treatment mechanisms that could work on lithium at these low levels, then they could likely generate a source. And so on the right, you can see this is the depth on the y-axis and lithium concentrations on the x-axis. And so you can see the Anadarko Basin, the Smackover here up to 400 or 500, 450 parts per million, and then the Deep Edwards, high concentrations in those basins. Brent, do you want to add anything to this?
Just that, since this study was done, there have been a number of analyses that have been published by Standard Lithium and some of the other companies working in the northeast part of Texas. Some of those lithium ppm values exceeded 850 ppm, 600 ppm. So there's a lot of really high values that are coming in, but the sample density in northeast Texas is far less than, say, the southwestern Arkansas area. So and it's just because those wells, there's the old legacy fields in the Smackover north of the Haynesville in northeast Texas, and so they're old stripper wells that produce a lot of water and very little oil, and so there's just very few active production going on, and so it's going to take a lot of effort to actually get samples from northeast Texas compared to a lot of the other areas. One of the other areas that you were mentioning, the Anadarko Basin, has historically had some values from the USGS produced water database that had elevated values as well for lithium.
But you weren't able to confirm those with recent analysis.
No, but the Eagle Ford had some values that were between 200 and 300 ppm that have shown some promise. But there's, again, sample density across the entire Eagle Ford that extends from southwest Texas to all across to East Texas. We just don't have a whole lot of data points to see any kind of consistent results and to see what those ranges might be in the southern parts of Texas.
Thanks, Brent. And so another aspect of the study was to look at infrastructure, and of course the Gulf Coast is well served with roads, and this is the orange lines are the highways, and then the brown are the interstates, and then the rail lines. So very well developed, and so that should not be a constraint on critical mineral or rare earth development in the Gulf Coast. Brent?
Yeah, it's a major advantage, I think, for the Gulf Coast area to have all of those ports and to be served by 5 Class 1 railroads, that facilitate movement of materials, and basically the infrastructure is very well developed in the Gulf Coast region.
And I guess one aspect of that, Brent, is that Linus is potentially developing a site for processing near the coast, and could import stuff then from other parts of the world to process. Is that that's one of the advantages?
Right there on the mid-coast of Texas, I think there's a blue dot there that looks very close to where that Seadrift location is, and kind of down to the south, that one right there. That's about where Seadrift is, and that's where Linus is building that DOD-funded that rare earth element extraction facility here in the near future. So one of the things that we also looked at was the location quotient. And you kind of compare different industries across the Gulf Coast region with the national average. And as you look at things like the employment location quotient or the wage location quotient by comparison. And so if we were basically on average with the rest of the nation, we'd be at a 1. If you're less than a 1, then you're below average or not as ready as the rest of the nation. And if that number was to exceed 1, as you can see from the employment location quotient in that third column, most of the numbers there exceed 1. And some of them 5 or 4, depending on which sector of industry we're talking about. So we tried to look at all of the mining and oil and gas, the infrastructure that would be able to support, the critical mineral extraction and processing and development within the region. And all of those are very favorable for the Gulf Coast region, especially on the wage location quotient area. For many of those sectors, we're well above the rest of the nation on average.
Thanks. Nolan?
Yep. So one of the things that we were looking at is essentially for processing, or for essentially what can we do with the lignite and the lignite-based rare earths, and how can we produce that into a product? To start with the carbon ore, the CO part of the project, we wanted to talk about what can be done with the lignite itself. There's considerable work that North Dakota, both the ERC and the college, as well as other groups, have been looking at for processing of lignites into carbon products. A couple of major uses are as graphite or building materials, and one specific benefit of the extraction process from lignite is it actually purifies the organics within the lignite to a point of below 0.5% ash in those organics, where the material then is the high purities needed for graphitic use. As a note, the extractive performance of the rare earths, once again, as shown earlier, is very similar to what the North Dakota lignites are. And so we expect that the Texas lignite would be extractable with the existing processing that we currently have. It may have slightly reduced performance as the comparison, but in essence, we'd need a lot more specific testing with the lignites to confirm that. But some of the benefits of that, if that's true, that the Texas lignites are processable, is essentially it takes advantage of the existing processing facilities and technology developed by UND. This would potentially reduce timelines by as many as 5 years. An operational pilot already exists for processing lignite. It leverages more than $20 million in technology and equipment development efforts that have been completed already. And it presents a path to monetizing rare earths and carbon products from lignite in the near term.
Right, that's fantastic, and we hope we'll be able to leverage all your hard work, Nolan, and skip ahead. And there is one mine in Louisiana that is uses its coal for activated carbon, right, Brent? I can't remember the name of it, but
right, ADA is the name of the company in Louisiana.
Right. So, as we saw from the prices earlier, having additional products with the rares would be very important for economic viability.
Yeah, both from a recovering more value from the material, but also from a stabilizing price. So your entire revenue isn't based off of the fluctuating price of rare earths. You have something that has a bit more of a concrete price behind it. So kind of just a quick brief on the North Dakota technology. So we've been developing this since 2016 with lab scale, where we confirmed that the rare earths are in the organic phase, and we developed a process to extract specifically from that organic phase, leaving all the minerals behind, patented that. From that, we then moved that to a bench scale where we could produce high purity rare earth mixtures, not just extracting from the lignite, but getting them eventually to products. And then over the last few years, we've been moving that to our pilot scale of half of a metric ton per hour throughput to demonstrate it at a continuous process and validate economic feasibility. as a note on that pilot, the pilot has thus far run 140 tons of lignite through it, from at least 4 different sources. And we've produced there was an entire week of production where the products produced were of qualities for direct refining and sale to refiners.
And on the right, Nolan, you show various companies that I guess you're working with, and I know we both talked with rare earth salts. Maybe you could describe a little bit. So you would send the oxides then to rare earth salts, and then they would refine it to generate the elements.
Yeah. As of right now, UND's technology stops at the production of a mixed concentrate. And yeah, all the companies and groups to the right are the sponsors, partners, and supporters of the technology to date in its production to its current state at that pilot scale. But the particularly rare earth salts or other refining companies would be the offtake for those rare earth concentrates from the lignite-based resources. Just essentially some more discussion on the pilot. And once again, it was about that 0.5 ton per hour. Ultimately, for a 300 ppm resource, that'll produce about 3 to 5 kilograms of rare earths per week. And typically in the elevated concentration lignites that have significantly more of the magnet rare earths, that can produce up to 1 to 2 kilograms of those, which would essentially be enough for an electric vehicle per week. And once again, this is producing a concentrate. The rare earths and also a number of other critical minerals, such as germanium and gallium, are collected into a concentrate, not ultimately purified directly in that process. Although existing processes would work for that separation. Then finally, the pathway to carbon products. There's a significant amount of carbon products currently manufactured from lignite and loot-rank coals. One notable aspect is humic acids. That primary source for humic acids today is leonardite and lignite. They're typically used in the agricultural industry, but also in pharmaceutical industries. And that market today is approaching $1 billion in size. Additionally, XMETs and Blastics and Microbeam both have technologies confirmed to make structural material from lignites, which is another high throughput possible use rather than just purely high value uses. And then also the UND's ERC and George Washington University have all developed processes for battery grade graphite from lignites. So there's a significant amount of carbon products that can be produced from lignite coal.
Yeah, I think when Sim Plastics visited us, they showed us some roof tiles that they developed, and they're supposedly much stronger than conventional roof tiles. So Brent, do you want to?
Sure. As part of the technology innovation centers, and one of the tasks we have is to develop and try to coordinate and collaborate with different industries across the region. So one of them that has been, very good with us is Element USA. They're a rare earth element and critical mineral extraction technology incubator that had a facility in Gramercy and in Louisiana, and they've since moved their facilities and built out a 26,000 square foot facility here in Austin, Texas, near the university. Maverick Biometals is one that has developed an enzyme for hydrolysis techniques for critical mineral and rare earth element extraction. They're based out of San Antonio in Texas. EnergyX is a battery technology and lithium extraction company, and they're working on kind of produced water and focused on some of their facilities, that their pilot plants that they have down in South America, but they're planning on moving those into the produced water sector, working with oil field operators. And then, of course, UT Austin's Petroleum Engineering Department, they've started to work on critical mineral and rare earth element extraction from various feedstocks. Blue Line Corporation is a manufacturer of inorganic rare earth salts, that Nolan had mentioned for separation of non-solvent extraction technologies. Semi-plastics for looking at manufacturing roof tile and materials from carbon resources, and then Microbeam Technologies, that specialize in alternative uses of carbon ore and extractability of rare earth elements and critical minerals from carbon ore material. So it's been very successful in kind of building these relationships with these companies, and hopefully going forward, working with them in the future for future phases.
All right, and we really appreciate all of their support, and we're very excited about the opportunities upcoming. And so another aspect of the work was the stakeholder outreach and education. And we had a stakeholder advisory committee that included various state agencies and companies that we met with at the beginning part of the project to develop the plans and the goals and stuff. Then we also had webinars that were recorded and are available on the website, and including Nolan's webinar on North Dakota lignite, and also an ETL webinar on prediction of subsurface reservoir properties using AI and machine learning. And then Mark Lochmelis and others will be hosting a webinar in August this year, August 13 and 14, North American Workshop on Critical Mineral Research, Development and Education at the Jackson School. And then various people in the team published different papers, and the website, this is the website. And then an example of one of the papers is coal ash resources and potential for rare earth element production in the US that Bob Reedy led, and that received a lot of attention, as estimating $8.4 billion worth of potential material from coal ash in the US. And then, this is a reconnaissance effort. This was the first phase of the program in the Gulf Coast, and we're way behind really where North Dakota and Wyoming and other states have been looking at coal for rare earth elements and critical minerals. So we had a limited number of samples. In comparison, we had about 120 samples in North Dakota. Williston Basin is about 2,500 samples. So we need to do a lot more sampling and analysis, and very limited coal ash samples because it's difficult to access the coal ash from the power plants. But we hope in the next phase that we will be able to do more work. And then working with Nolan and his team, we hope to look more at the mode of occurrence of the rare earths and confirm that, it's in the organic phase, in the lignite, and additional work on extractability. And then Brent and others have a lot of ideas about the bauxite residue. It looks very promising, more than 10 times the concentration of the upper continental crust. And looking at those beds, look at the stratification of the rare earths and the variability among the sites. It's nice that the Copano site derived most of its bauxite from a single, am I trying to say, from one side, one region, and so maybe fairly uniform. And we need to look at the extractability of rare earths from the red muds. And then the team would be very involved in looking at heavy mineral sands, graphite and zeolite, and looking at more work on lithium in produced water, and increased interactions with processing and manufacturing companies, and workforce development and training of students. We have two new people, Mark Lochmelis and another in the Jackson School that focus on critical minerals and rare earths. So Brent, you will be leading the second phase. You want to describe?
Yeah, so the second phase kind of builds on all the work from phase one that Bridget led through the Gulf Coast region, but it's focused across Alabama, Mississippi, Louisiana, Texas, and then New Mexico, south of the San Juan Basin. It basically takes advantage of three different areas. There's still the coal material and coal ash that we're going to continue to develop. There's the area of produced water as a major focus, and looking at all of the kind of the lithium and critical minerals in produced water, because it's such a huge volume, especially here in Texas with the oil and gas production as a waste stream. And then the other category that includes bauxite residue and zeolite and heavy sands and all the other stuff, and even the material that's in the subsurface that where oil and gas formations are, the sedimentary rocks that could host critical minerals or rare earth elements. Those have potential, and so we're going to explore and characterize those to figure out if that can be a feedstock moving forward, and what kind of possibilities there might be. So it really kind of builds on everything that's been done before, but expands it, and then continues those collaborations with industry and building the workforce to, from different areas in order to facilitate rare earth extraction and critical mineral extraction within the Gulf Coast region.
Thank you so much for listening. If you have any questions, don't hesitate to reach out. So thanks, everybody.